To derive the demand function for a consumer who says that she has Cobb-Douglas preferences, we set up a maximization problem, and I prefer to use the Lagrange method. So we have a problem that is maximizing the utility as a function of the two goods. So in this case, the Cobb-Douglas function, y1 raised to alpha times y2 raised to beta, and we're going to maximize this with respect to both of those two goods. And we have a constraint in the given to us by the budget constraint, so we will know that we can spend all the money we have but nothing more than that. And since we have a Cobb-Douglas preference, we know that we're going to end up in an internal solution, and therefore we can set it as an equal sign here. So we create the Lagrange function, and the Lagrange function is a function of the two goods and the Lagrange multiplier, which we use lambda to represent. So we have the function we want to optimize, and then we have the constraint after the multiplier. We calculate the first order conditions, so we derive the Lagrange function with respect to the variables and the Lagrange multiplier, and then of course set the partial derivatives equal to 0, so we know that we have reached an optimum solution. So we see here that the first order condition 1, that's the partial derivative of the Lagrange function with respect to the first good, will give us the marginal utility for good 1, which is expressed like this, minus lambda p1, and we set that equal to 0. So you can rewrite it, if you will, as marginal utility of good 1 equal to lambda p1. You take the second first order condition, you take the partial derivative of the Lagrange function with respect to the second good, and therefore you will end up with this expression, which is the marginal utility for good 2, minus lambda times p2. And then you take the first order condition number 3, which is with respect to the Lagrange multiplier, and that will always give you the constraint back. So if you have done something wrong when you set up the Lagrange function, you will notice that immediately here. So in this case you will have the constraint back. And so you see here that you have minus p1 1 minus p2 y2 plus m is equal to 0. So we have the right one. If you like, you can rewrite these two, the first and the second one. You see here that you have a lot of letters to look at. So you have alpha times y1 raised to alpha minus 1, and y1 raised to minus 1. That is equal to something divided by y1. And if you take away this minus y1, you have the original utility function. So you can multiply alpha times the original multiple utility function divided with y1, and set that equal to lambda p1. And then you do the same thing with the second function here. So you have beta times the original utility function divided by y2 equal to lambda p2. And the reason that we do this is that this will give us an easier calculation in the next step, because we will have here alpha times the utility function divided by y1 divided by beta times the original function divided by y2. So what we have is alpha, since these two cancels out, we will have alpha divided by y1 divided by beta divided by y2. So you will have alpha y2 divided by beta y1, which will be the same as we will get in a couple of minutes. So the next step is that we calculate, we let the first order condition number 1 be divided by the second first order condition. So what you have here is the marginal utility for good 1 divided by the marginal utility for good 2, and that is equal to lambda p1 divided by lambda p2, so the lambdas cancels out. So what we have here is that this is the marginal rate of substitution, which is the slope of the indifference curve, and that has to be equal to the slope of the budget constraint, so to be able to achieve a utility maximizing bundle. So we know that we are at the right position. So we calculate through this or rearrange it a little bit. So we see here we got this, as I mentioned above, the alpha y2 divided by beta y1 equal to the relative price. So you can rewrite that into P1 y1 equal to alpha P2 y2 divided by beta, or, now a page break, so in a little bit longer hop, jump here, or you can have it as, if you calculate P2 y2 as beta P1 y1 divided by alpha. So you do either. And then you put that one into the first order condition number 3. So for instance, we substitute P1 y1 with alpha P2 y2 divided by beta, and then we can solve this for y2. So here we got it. Substitute P1 y1 with this expression, and then we have P2 y2 equal to m. So we see that the simplest case is to first multiply with beta. So we will get rid of the divided by beta there. So we have beta P2 y2 equal to beta m. That gives us alpha times P2 y2 and beta plus times P2 y2. So we will have alpha plus beta times P2 y2 equal to beta m. So when we solve this for y2, we will have beta m divided by alpha plus beta times P2, like that. So the optimum the demand function for good 2 as a function of the prices for the two goods, P1 and P2, and the income will be beta divided by alpha plus beta times the income divided by the price of the second good. So we substitute this one into the first order condition 3 again, the budget constraint. So now you got P1 y1 plus P2 times times y2 star, the optimum demand function for y2. And we see directly that P2 cancels out, so we'll have and then we multiply through with alpha plus beta. So we'll have alpha plus beta times P1 y1 plus beta m is equal to alpha plus beta m. So alpha plus beta P1 y1 is equal to alpha m plus beta m minus beta m, and then of course alpha m. And then we solve it for y1. And we then get y1 star, it's the demand function, and the function then as a function of P1, P2, and m will become alpha divided by alpha plus beta times the income divided by the price of good 1. So you see here that the final solution is that we have these two demand functions, demand function for good 1 as a function of P1, P2, and m, alpha divided by alpha plus beta times m divided by P1. And as you see, we don't have any P2 inside here whatsoever. So whatever you do with the price of good 2, that doesn't affect the demand for good 1 when you had Cobb-Douglas preferences. So the cross price elasticity will be equal to 0 for these goods. And we have the same expression, or the similar expression for the second good as a function of P1, P2, and m, beta divided by alpha plus beta times m divided by P2.